an email about the hour, and of course I have to have a answer. Thank you for that. And it's stuck. Yeah, it doesn't work. Oh yeah. Okay, this is overview of my talk, and I'm basically going to talk about parallel search. And for the last 10 years, the quality of administrations has improved significantly in order to achieve a high performance scenarios. However, having a high performance system still remains as a challenge because of two reasons. One is related to the performance bottleneck caused by CPU and memory requirements, which is not enough to build a good planner. And the other reason is that we would observe the diminishing return even if we improve heuristics. Therefore, it is quite necessary to have different approach in order to speed up the planning system. And it is quite natural to incorporate parallel search into the planning system because of several reasons. One is everyone uses search methods in order to have high performance planners. Another reason is that search is the most computationally intensive part of the planning system. And parallel computing has become the fact standard concerning the fact that we have multi-core CPU machines as well as we have PCs connected by networks. Also, it is clear that parallel computing provides more CPU and memory resources in order to solve hard problems. And finally, the speed of individual CPU core doesn't increase as rapidly as that used to be, which means that in order to get the speed up from the hardware technology, it is quite necessary to parallelize the search algorithm. So we are working on parallel search, which is called HDA star, and we applied HDA star to a high performance optimal planner, which is fast downward plus margin shrink abstraction heuristic. And in the paper, we wrote that we achieved 64 speed up with 128 CPU cores, but I have more results to show you in the last part of this talk. And of course, we have more memory available. We are able to solve more problems that are solved by parallel search only. However, it is quite attractive to have parallel search. There's no free lunch. The task is the difficulty is how to distribute work while avoiding the severe overhead that happens only in parallel search. And there are mainly three kinds of overhead that happens in parallel search. And one is called search overhead, which is a ratio of extra states that are not explored by sequential search, but explored by parallel search. And another overhead is called synchronization overhead, which is like idle time wasted at the synchronization points, including the locks on shared memory machines. The communication overhead is mainly caused by network communication, which is like extra cost to exchange information. And unfortunately, these overheads are not dependent. They are dependent. And it is quite difficult to find the best case scenario theoretically. And so many practitioners try to measure a lot of experiments in order to minimize the overhead and then increasing the maximizing the speed up. Because this kind of thing is quite related to the platform, let me explain the environment where I have been working on. Tsubame is a machine which consists of over 650 nodes connected by InfiniBand, and each node has 16 cores with 32 gigabytes shared memory, resulting in over 10,000 CPU cores, which is ranked at the 41st top 500 all. And the biggest problem when parallelizing search is it incurs communication overhead in order to access memory on other nodes. And this one is not related to the research issue, but Tsubame is of course so expensive that it is shared by hundreds of researchers, meaning that, the schedule is less than batch, and I have to wait for a long time to my job to be executed, and I can rent a lot of nodes, but it incurs a usage cost, so I need money. And on this platform, and there's also a problem related to parallel SR search. The fact is that the search space of many planning problems is not tree but bad. So more than one path can lead to the same state. This causes a problem when parallelizing algorithm. Assuming that we have two processors, P and Q, and these nodes are assigned like that, and then if we don't share anything, and if P explores the search tree below state D and Q explores the search space below state D, we have duplicate search, which doesn't happen in sequential search because of the closed list available. So on the other hand, parallel search must search twice if we don't share. As a result, we want to share something by having some overhead. One natural way is to have what is called a distributed closed list. And in this method, each processor has a part of the closed list, which is a disjoint. And by combining these closed lists, this can be seen as a very big closed list. And for example, in this case, each processor has 3 entries. In total, it has 6 entries, a larger closed list. And now we can detect the duplication. But the problem is that assuming that Q is searching below D, and Q marks that D is searched by Q, then what processor P must do is that first it must send a message to ask the information on D to the processor Q, because D is located there. We need communication here. And then by the time when the information on D comes back to P, we have processor P must wait, which incurs synchronization. And processor Q occasionally checks whether this kind of message arrives, and if it receives, send information back to P, which needs another communication. So in summary, what I'm saying is that this approach needs two communications, and also we need to wait, which degrades the performance of the parallel search. There's one way to cure this problem by using work distribution strategy based on hash keys, which is also known to game researchers as the name of translation table-driven work scheduling, TDS. In the previous slide, what happened is that first we distributed work, and then we considered how to share data. In TDS, instead of doing so, TDS just moved the work where the data is located. Okay, let me explain that with this example. We can still use distributed closed list, like that. And then we change one rule about the work distribution strategy. A must be searched by processor P, because A's information must be located here. And when processor P expands 3 nodes, this node must go to Q, because because this is located here, while the other two nodes remain here because these entries are here. And this strategy happens recursively until we find a goal. And the good news is that we can find duplication. The reason that if processor Q creates a node of D, a state of D, and while he creates a state of D as well, these two states must go to Q because these entries here. So processor Q knows whether we have duplicates or not, and by doing so, we can predict duplication. And I use this TDS idea because to A-star search because TDS was originally invented in IDA-star. And the algorithm is quite simple. We prepare open closed lists that are maintained locally by each processor, and each processor selects a state in the local open list, and it generates successor feed, and then sends that successor to the processor that must expand. And there are several ways by using this idea. One is we can avoid duplicate search, as I explained. And another thing is that we can use more memory for open closed list as we have more processors. I know that many people worry about the box distribution, but we don't have to worry about that so much because there's one very good hash function which is quite popular among game researchers. And I'm using this function to achieve load balancing. And another worry is about communication overhead. But this is not an issue because we can pack several states into one to send it out to another processor. And the most important point is asynchronous communication. Because once we send work, we don't have to wait. We can just work on the next node in the open list immediately after sending out the work to its destination, resulting reduced, and we can basically remove all the synchronization overhead by doing so. And one more is that actually PRSR is also PRSR based on similar ideas. But because of the hardware limitation, it was a synchronous algorithm, which means that we have to wait until receiving a state. And as asynchronous conference, it can sometimes become slower than sequential search because of this overhead. And there are some other implementation issues, but there are about solution optimality and termination reduction, but these are quite technical, so I'll skip this. And let me explain the experimental results. I implemented this one I ran experiments on Tsubame, and I used fast downward plus margin shrink abstraction. And I used MPI and Decimal, which is a part of Google performance to implement HDSR, while I used Bootstrap plus inline assembly operation to write a faster log operation, and plus I also used the Google performance in order to implement PRS for comparison. And I limited the abstraction size for margin shrink abstraction to the size of 1000. And okay, I didn't include the time for the abstraction because I didn't parallelize that one. So each processor replicates the abstraction table. And I used a lot of test suites from the ICAPS competitions. And this is the speed up with up to 128 CPU cores. And I used many instances from the competitions, and in the best case, the speed up was something like 64 with 128 processors, and the worst case was something like 30. And the fact is that these problems have become so easy for processors to solve already. And it becomes quite difficult for parallel search with over 100 to find good place to parallelize. As a result, the performance degrades. And I also compared the performance of HD star against PR star by using the CPU cores. And this is a number of, this is the speed up for HD star, and this is the speed up for PR star. And this is for each program, and if this plot is below this linear line, that's a win for HD star. HD star is faster. But if this plot is above this line, this means that PRA star was faster than HD star. And as you can see clearly, HD star wins by a large margin. And the reason is quite simple. I checked the CPU usage for these two algorithms, and in HD star, all the processors are almost always busy, while we can see some idle time for PR star, which is caused by synchronization of I. And after writing the paper, we rented the cluster with over 500 CPU cores, and I measured the experiments. And HD star still scales well with over 500 cores. And in the best case, HD star achieved like 374 speedups, and on average, I think the number is something like 200. And in the worst case, it achieved only 50. But again, this was quite hard for HD star to parallelize with a larger number of processors because it has already become easy with 64 processors. And I checked about the search overhead to see where the bottleneck comes from. And it's quite correlated to the solution length. And this is the solution length, while this is the search overhead. It's extra state, the ratio of extra states searched by parallel search. And actually, the search overhead becomes bigger with a longer solution and with a larger number of processors. And actually, these programs are solvable. The reason that, actually, this is not so surprising to me because the branching factor in solvable is something like between 2 and 3, and each processor needs a lot of speculation because each processor knows only its local operators. As a result, the search overhead increases. And one more thing that I should tell is that more problems are solved by using 5 CPU class because it has 1 terabyte of memory. And boosting up the performance of the solver in salt domain especially. And actually this is a new problem, so I will try that. And because I'm running out of time, I should finish up. And my conclusion is that the HDSI is applied to optimum planning and achieves about 374 speed. There are 3 things that I want to do, and I want to invent a new technique that is suitable for grid environment. And because I haven't used any feature for the thread-based approaches, I want to use TLSR, and I want to combine with the latest state-of-art heuristic, which is called random tax heuristic. Thank you very much.
We are perfectly on time. We have a few minutes for questions.
So the heuristic you're using has a very low evaluation cost per node for research. Have you studied how the speed that you get depends on how long the heuristic evaluation phase takes?
You mean in this method, heuristic is pre-computed, right?
Yes, it's really cheap.
And I haven't had any answer yet, so maybe I would know after doing this. Yeah, I'm sure that I don't know that yet.
So you use the Hilbert's hash function in the distribution, the search node. So it seems a perfect hash function would uniformly distributing the nodes into different search nodes into different computer nodes in a form factor. So
Yeah.
if you have 100 computer nodes,
Yeah.
the chance of generating success that would map back to the local node is only 1%.
That's right.
So 99% of chances, assuming a uniform distribution, generate a successor will be uniformly generated throughout the search space, then 99% chance you will be mapped into a remote node. Right? So
Yeah.
it seems that doesn't scale very well. So the number of links between two computer nodes will be basically quadratically in the number of computer
Yeah,
nodes.
I'm not sure how hardware is constructed. So I don't know, but anyway, it's connected by each-one, that's one good point. And now I'm measuring experiments with 64 nodes, and I'll see whether the performance varies with communication over them. Yeah,
So 64
4 nodes.
So each
Oh,
node has
64 nodes and 64 CPU cores with 64 nodes.
okay.
So I'm doing that experiment, but I haven't obtained that yet.
Thank you.
Yeah, but the good thing is that we can work asynchronously, which hides a communication delay, which is a good part. So I'm not sure, so I'll see that. Yeah.
Yes.
Yes, in the presentation you said that the communication code is not a big deal, but maybe it's good for like classical problem. But for example, for conformal problem or for some other planning problem, when the state size, the size of the state is huge, so do you think any solution for that? Because there are too much traffic between the core.
Yeah, I think because still the size of the state is not that large, like 1 megabyte or 10 megabyte.
Yeah.
Kilobyte, right?
The size of state is not a big deal if it's for a classical problem, but for other type problem, it's really, really big, much bigger than that could be a problem. I mean, the size of the state for other type of planning problem is much bigger than the state in a classical problem. So in that case, I think you will have a problem in this solution. So what do you think about that?
So I can't.
Okay.
Maybe we can talk offline.
Okay. The size of the state.
The size of the state.
Yeah, the state, the size of the. I mean the size of a state in a classical problem is not big. Yeah, so the communication between the node is not a big deal. But for other type of planning problem, the space size is much bigger.
How much bigger is that?
It's exponential time.
So it's not, but once, how can I say? If the size is like kilobyte or megabyte, that's not a very big issue. Because the problem when writing the parallel program is that the overhead to send is quite high.
Yes, but the solution is Scalable to exchange space between the core, right? Between every core. And then when you some for two other cores, the space in classical not a big, the size is more. But for for planning program, the space is much bigger. And in that case,
Okay, we'll talk about that offline because I don't know how